What is electricity? It is a powerful form of energy. It flows unseen all around us. It lights up our cities at night. It runs the machines in our factories. Our entire modern life depends heavily on it. Electricity is truly an amazing phenomenon. It fundamentally changed everything for human civilization. It continues to shape our collective future. Imagine a world without this invisible power. Nights would be profoundly dark and still. Our food would spoil much more quickly. Communication across vast distances would be slow. Factories would grind to a halt. Our carefully constructed daily routines would collapse. Life, as we know it, would be very hard. The comforts we take for granted would vanish. We rely on it more than we often realize. But electricity is not some form of magic. It is a fundamental force of nature. Scientists and thinkers studied it for centuries. We gradually learned how it works. We then learned to harness its immense power. This crucial understanding utterly transformed our society. It continues to be a primary driver of innovation. New discoveries about it are still being made. Our journey with electricity is ongoing. Look around your own home for a moment. The television screen glows because of electricity. The computer you use needs it too. Your kitchen appliances all rely on it. Hospitals depend on it to save lives. Electricity is truly everywhere in our modern world. It is the quiet, unseen worker. It makes our convenient modern living possible. It is a cornerstone of our technological age. Let's explore the concept of electric charge. All matter is made of tiny particles. These particles include electrons and protons. Electrons carry a negative electric charge. Protons carry a positive electric charge. Opposite charges attract each other strongly. Like charges, however, repel each other. This fundamental interaction is a basic rule of physics. It underpins all electrical phenomena we observe. Electric current is simply moving electric charge. Think of water flowing steadily in a river. Electrons, the charge carriers, flow through wires. This continuous flow of electrons is the current. We measure the strength of this current in amperes. More amperes signify a greater flow of charge. This is the useful electricity that powers devices. It is the lifeblood of our electronic world. Without current, there is no active power. Voltage is like the electrical pressure in a system. It is the force that pushes the charges along. It compels the electric current to flow. Higher voltage means there is more push. We measure this electrical pressure in volts. Voltage is the force that drives the electricity. This push helps overcome any obstacles to flow. It is also known as potential difference. It's essential for moving charge through a circuit. Resistance is something that tries to stop the current. It is like friction acting against electricity's flow. Some materials resist the flow of current a lot. These are called insulators, such as rubber or plastic. Other materials let current pass through them easily. These are known as conductors, like copper or silver. Resistance is measured in a unit called ohms. Understanding resistance helps us control electricity. It allows us to design safe and effective circuits. Electricity manifests in two main forms. One common form is called static electricity. This occurs when electric charges build up on surfaces. These charges do not flow in a continuous path. Think of rubbing a balloon against your hair. The balloon might then stick to a nearby wall. That is static electricity in action. It is a temporary accumulation of charge. It can be quite surprising sometimes. Static electricity can often surprise you unexpectedly. You might feel a tiny, sharp shock. This happens when the built-up charges suddenly jump. Lightning is a massive spark of static electricity. It is nature's powerful and dramatic display. This discharge occurs between clouds or cloud to ground. It is a very visible example of static discharge. The forces involved are truly immense. It reminds us of nature's raw power. Current electricity is quite different in its nature. In this form, electric charges flow in a steady stream. This continuous flow usually happens within a circuit. This is the type of power in our homes. It flows silently and invisibly through wires. It powers our lights, our computers, and our gadgets. It provides a continuous and reliable energy supply. This is the electricity that runs our modern world. It is incredibly versatile and useful. Current electricity itself can be DC or AC. DC stands for direct current. In DC, the electric charge flows in only one direction. Batteries, for example, provide DC power. AC stands for alternating current. In AC, the current changes its direction rapidly. Our household wall sockets typically supply AC power. Both DC and AC are very useful for different purposes. Each has its own specific applications. So, how is this useful electricity actually made? One common way involves mechanical methods. These methods use motion to generate electricity. A spinning wheel, for instance, can make it. This process happens inside a device called a generator. Think of a large wind turbine out in a field. The wind spins its long blades around. This rotational motion creates electrical energy. Many power plants utilize this fundamental principle. Large-scale power plants often use massive turbines. Water flowing through dams can spin these turbines. Steam produced by boiling water also spins them effectively. The spinning turbine is connected directly to a generator. The generator then converts this motion into electricity. This conversion is called electromagnetic induction. It is a key principle discovered by scientists. It forms the basis of most electricity generation. Motion is transformed into electrical power. Chemical methods for generating electricity also exist. Batteries are a very common and familiar example. Inside every battery, specific chemical reactions occur. These controlled reactions release energetic electrons. The newly freed electrons then flow out as current. This is how portable devices get their power. Your mobile phone uses a battery. Your television remote control does too. They provide power on the go. Fuel cells represent another promising chemical method. They are somewhat like special refillable batteries. They require a continuous supply of fuel, like hydrogen. They combine this fuel with oxygen to make electricity. This process generates electricity very cleanly. Water is often the only byproduct produced. Fuel cells are not as common in daily use yet, but they hold significant promise for future energy needs. Research continues to improve their efficiency. Section 5, harnessing nature's power, solar and thermal generation. The sun, our nearest star, gives us abundant energy. We can learn to turn direct sunlight into electricity. This amazing process is known as solar power. Special devices called solar panels do this important job. These panels contain many photovoltaic cells. When sunlight hits these special cells, something happens. Electrons within the material get excited and flow. This controlled flow of electrons creates electric current. It's a direct conversion of light to electricity. Solar power is considered a very clean energy source. It does not pollute the air we breathe. The sun's energy is essentially free for us to use. It is a resource that will not run out. Many homes around the world now have solar panels. Large-scale solar farms also exist in sunny regions. These farms can power entire communities. This technology is rapidly growing and improving. It offers a sustainable path forward. Thermal energy simply means energy from heat. We can use various sources of heat to make electricity. Geothermal power plants use the Earth's own inner heat. Hot steam or water from deep underground is utilized. This steam rises and turns powerful turbines. This is also a renewable source of energy. The Earth's core remains incredibly hot. This heat is a constant and reliable source. It's like tapping into the planet's own furnace. We also commonly burn various fuels to produce heat. Fossil fuels like coal, oil, or natural gas are burned. The intense heat from this combustion boils water into steam. This high-pressure steam then spins large turbines. The spinning turbines, in turn, make electricity. This method is widely used around the world, but burning these fossil fuels causes air pollution. It also rapidly uses up finite natural resources. This presents a significant environmental challenge. Section 6, the atomic heartbeat, nuclear energy's role. Nuclear energy is another very powerful source of electricity. It originates from the very core of atoms. Atoms are the tiny building blocks of all matter. We can split the atoms of heavy elements like uranium. This specific process is known as nuclear fission. When a large atom splits, it releases huge energy. This released energy is primarily in the form of heat. It is a highly complex and controlled process. It unlocks the power hidden within matter. Nuclear power plants are designed to control this fission. The intense heat released from fission boils water. This process creates large quantities of high-pressure steam. The steam then forcefully spins enormous turbines. These turbines drive the connected generators. The generators then produce the electricity we use. The latter part is similar to other thermal plants. The unique aspect is the source of the heat. It is a testament to human ingenuity. Nuclear power offers certain distinct advantages. It does not release greenhouse gases during operation. This is beneficial for maintaining air quality. However, it does create radioactive waste products. This waste is hazardous to living things. It must be stored securely for very long times. This long-term storage is a major challenge. Safety at the plants themselves is paramount. Accidents, though rare, can be catastrophic. People often debate the merits of nuclear energy. It provides a substantial amount of power. It has relatively low carbon emissions during generation, but the risk of serious accidents is always present. The disposal of nuclear waste is an unsolved problem. Scientists are actively seeking safer nuclear technologies. The future role of nuclear power is still uncertain. It remains a contentious topic in energy discussions. Balancing benefits and risks is crucial. Section 7. The machinery of power, components of generation. Electricity generation systems have several key parts. First and foremost, there is an initial energy source. This source could be the sun, wind, or water. It could also be fuels like coal or nuclear material. This is the fundamental starting point for generation. This primary energy will then be transformed. It is the raw material for making electricity. Without it, the process cannot even begin. The choice of source has many implications. Next, there is often a device called a prime mover. This is a machine that turns energy into motion. A turbine is a very common type of prime mover. An internal combustion engine can also act as one. It takes the initial energy from the source. It then creates useful mechanical movement or rotation. This resulting movement is a very important step. It bridges the gap between raw energy and electricity. Different sources use different prime movers. The generator itself is the heart of the system. It takes the mechanical motion from the prime mover. It then skillfully changes it into electrical energy. Most generators use the principle of magnets and wires. Spinning magnets create an electric current in coils of wire. Or coils of wire spin within a magnetic field. This is how the magic of generation happens. It's based on the laws of electromagnetism, a truly remarkable piece of engineering. Finally, there are crucial control and transmission systems. These systems carefully manage the electricity produced. They ensure it is at the correct voltage and frequency. Large transmission lines then carry it to users. These are often big power lines on tall towers. They transport electricity over considerable distances. It is a complex and interconnected network. From generation to your home, it's a journey. These systems keep the power flowing reliably. Section 8. From source to socket, the journey of electricity. Electricity we use travels a surprisingly long way. Its journey begins at the massive power plant. Here, various forms of energy are converted into electrical form. The plant's generators produce a large amount of electricity. This electricity is initially at a very high voltage. Using high voltage helps to send it over long distances. It significantly reduces energy loss during transmission. Efficiency is key in power distribution. This high voltage is not safe for direct use. Special devices called transformers are at the power plant. These transformers step up or increase the voltage. The electricity then flows into high voltage transmission lines. These are the tall metal towers carrying thick cables. You often see them stretching across the countryside. They carry electrical power for many, many miles. It is like an extensive electricity highway system. These lines form the backbone of the power grid. They connect distant power sources to populated areas. Near your town or city, there are electrical substations. These substations receive the high voltage electricity. Here, other transformers step down the voltage. They reduce it to a much safer level for local use. This electricity then travels through smaller power lines. Some of these lines are underground cables, others run on poles along streets and roads. This is the local distribution network. It brings power closer to consumers. Finally, another small transformer is usually near your house. It might be on a pole or in a green box. It steps the voltage down one last time. This makes it safe for your household appliances. The electricity enters your home through an electric meter. Wires hidden inside your walls carry it everywhere. You plug in an appliance and it works. The long journey of electricity is now complete. Power is delivered right where you need it. Section 9, our electric future, the imperative of sustainability. Electricity is absolutely essential for our modern lives, but how we choose to generate it matters greatly. Many traditional methods rely on burning fossil fuels. Burning coal, oil, and natural gas pollutes our air. It releases harmful gases like carbon dioxide or CO2. This CO2 gas traps heat in our atmosphere. This process is what causes global climate change. Climate change is a serious problem for our planet. It affects weather patterns and sea levels. Fossil fuels are also classified as non-renewable resources. This means they will eventually run out someday. We cannot continue to depend on them indefinitely. This is precisely why we need energy sustainability. Renewable energy offers us a viable alternative. Sources like the sun and wind will always be there. They are naturally replenished by the earth. They're also much cleaner for the environment. This is the path to a secure energy future. We must make a significant shift to renewable energy. This transition helps our planet to breathe easier. It directly fights the causes of climate change. It also means a reliable energy supply for the future. This important shift requires many new ideas. It needs substantial investments in green technologies. It also requires global cooperation and commitment. Nations must work together for this common goal. It's a challenge, but also an opportunity. Every one of us can help in this energy shift. We can all try to use less energy daily. We can choose to buy energy-efficient appliances. We can support policies that promote green power. Our collective future depends on these wise choices. A sustainable electric world is truly vital for humanity. It is one of the biggest, most exciting challenges. Powering our world without harming it is the goal. Let us embrace this responsibility together.